Hey y'all, happy Monday. I hope that we are all having a good day. Let's see, it's Monday, still Monday. It's gonna be Monday all day. It's raining here in Jacksonville, or it did earlier. Hopefully you guys will get here in just a second. Today we're going to talk about, we're gonna wrap up chapter 9. We are going to in a few seconds, I'll give you some updates about the exam and what's going to happen on Wednesday. And trying to think what else I have for you guys. Not a whole lot. I guess the biggest news is that I made cookies this weekend. I opted for some good chocolate chip cookies. There's definitely one on the desk in here, and I'm kind of wishing I could eat it like right now, but I'll wait till after class. So we'll start. If you guys have questions, go ahead and drop them in the comment box and I'll answer those. So Thomas asks, what percentage do we need on Alex to get full credit? So Alex is 2 components. So it's 200 total points. 100 points is your pi score. So if you have 80% of the pi complete, you get 80 points. The other half of that, so if you look on Canvas, it's the Alex pi and the on-time component. Those may actually come as 1 score. I don't remember. But the on-time component is that you have to, about AXE. I don't think you're dumb, but we may have called it something else, and I will double check on the Alex objectives about the one you're asking about. So on Alex, let me write that on the board for you guys. So for Alex, your pi score, so if you have 80% complete, you get 80 points. If you turn in on time 85% of the time, you get 100 points. So basically what this is going to say here for the on-time component is you need to have turned them in most of the time on time. So 85% of 138 is like 120. So you can have forgotten for like a week or a couple of things. Okay, back to the questions. Okay. So all right. So next questions. So AXE, if that's 2 things connected with a single lone pair, that is still linear. That also does not really exist. We did talk about AX and AXE3 and things like that. So if someone, when you get back in Alex, can send me a screenshot of that, I will send out information about that question. So now we have several questions. Okay, the exam. So for the next several seconds, we're all going to breathe, and I'm going to tell you about the exam. Okay, so exam 3 will be run through Canvas. There will not be a lockdown browser. Exam 3 is open notes. Now, notes are things that you have taken or handouts that you've made. Notes are not your friend, your mom, your brother, asking Siri to text your friend. You alone can use your notes. You can't use your friend's notes. You can't use anything else. So for the exam, it's going to be run on Canvas. It will open. Hold on, let me make sure I get all this right. The exam opens Wednesday at 3 p.m. and you have until Thursday at 5 p.m. So that means that if you want to use the full 80 minutes, you have to have started before 5 p.m. on Wednesday. So it isn't that you have to start by 5, you have to be done by 5. So that means that you need to have started by 3:30, I think. So you have 80 minutes, which is 10 more minutes than you would have in person, because I know that when you make me do something on a computer, it just takes me a little bit longer than it would on a piece of paper. So you have 80 minutes instead of 70. So it covers everything that we've done online, nothing in the past, nothing in the future, just what we've covered in line, and 9.6, which is a standalone YouTube video called Multiple Bonds. I'm going to send an announcement today with a direct link to that. We may talk about it some in here, but I'm afraid we'll get a little bit pressed for time, and that's important enough that we're going to add it in. So for the exam, it is up to 50% on Canvas, meaning I don't want to call it easy to grade stuff, but stuff that Canvas, the computer, will plausibly be able to grade. Multiple choice, fill in the blank. Matching would be something like that. So it will be up to 50% on Canvas. Those 50% are on Canvas. The other 50% will be another question that tells you to write your answers by hand on a piece of paper. So on that one, it will be it'll be a text box. Like, there won't be a place for you to upload your answer. You're going to upload that into another file, to another assignment. It has to be within 10 minutes of the other one. So a couple of you mentioned you were afraid, and I hear you. And so this is my solution. I'm not sure it will be perfect, and I'd like to apologize for internets and all the rest of that, okay? So because I'm afraid that if you try to upload it, it will somehow kick you out of the exam, finish everything in the Canvas first, then do the other one. When you finish Canvas, it will not let you go back in, but you will be able to upload in another window. Like, it'll be a second assignment. And in that second assignment will be basically a upload your handwritten work here. So on each page that you write on, you need to write your whole name. So you know how on the exam I give you 5 points to write your name on every page? I will do that again. So to make my life the most easiest, although if you don't have this much paper, that's okay, write a different question on each sheet of the paper. So like, I would write 1, and then at the top, Hannah Malcolm, that's my name. And then I would answer that. On the next page, it would be number 2, and then my name again, and then the answer. If it's a short thing, feel free to draw a line in the middle of the page and then write clearly that it's now number 3, okay? You will use Cam Scanner and then upload that PDF. So in the 80 minutes, you need to finish all the work. You can then go back and use your phone to take the pictures and upload that into the assignment, okay? So there's something else. It's open notes. I told you what it covers. I have posted the old equation sheet. I think I will try to put that in the Word document or in the exam. Canvas is a little weird, and so I'm going to do my absolute best. If you are concerned about whether or not you should withdraw from Gen Chem 1, the withdrawal deadline is Friday at 5 p.m. Our exam closes Thursday at 5. There are a lot of you in class, so I may not be able to, I know I won't be able to grade them all by Friday by 5, but I sent you a Google form link in yesterday's announcement. So the Google form, you can click on that and write your first and your last name, and I will grade yours as fast as possible. So you should get your score if you fill that out Thursday by midnight. Okay. That will work best if you turn it in before Thursday at 5, but that's okay. Okay, so we have a couple of questions. Sam asks, you have to complete the problem within the 80 minutes and then go to the other link on Canvas to upload it. So you have 80 minutes to finish the entire exam. But I'm afraid that if you try to upload a file and you did that first, instead of the multiple choice, that it will have a internet freakout and kick you out. So I'm going to have you upload it into another assignment that will literally just be, please upload your handwritten portion for exam 3 here. Caitlin asks, are the written questions on the Canvas assignment where we upload, or are they on the actual test? They're all in the test. Oh, I think that might have been Sam's question. So it will be, so you know how when you took my exam, it was like 10 multiple choice questions. Yes, it's all one file. It will be one Canvas quiz that the last question will be a series of, please write these up. So, sorry, I did not get that question out of this. Should we go ahead and complete both the Canvas portion and the written portion before submitting the Canvas section? So Ginger asks, should you complete both the Canvas portion and the written portions? So it's all in one assignment. So basically, if you opened the quip where you had to draw the flower and the duck, it will be like that, except you have 80 minutes. Some of them will be multiple choice. The last one will be a file upload. And then the file upload, you will upload somewhere else. I will try to make a fake quiz to give you guys an idea of what's going to happen. Hold on, let me find a piece of paper and write that down. I'll try to do that tonight. It will be optional, just so that you can see something. Fake 2045. So there's a couple of questions about the other part. So the file upload needs to be uploaded within 10 minutes of when you submit the first part, because a number of you tell me that that's the hardest part for you. Okay, so in the 80 minutes, you need to finish the exam. After that, it should take you 10 minutes to take any of those. You can do notes or Cam Scanner or anything that makes a PDF. So it just has to be a PDF. So if you tried to upload the quip last week and it didn't let you, then it's probably, which I didn't see any of these, it just has to be a PDF. So it will be restricted to a PDF because that's how I can grade it. So you can use notes, you can use Cam Scanner. Someone sent me an email that the Adobe app does it really easily. I don't care how you make a PDF. Shoot, y'all, if you own a scanner and you want to scan it in and upload it, I'm fine with that too. It just has to be a PDF and it will be in the second part. But there will be no questions in there. It will all be within the quiz part in total. Okay. So Sam, you can use anything you like. Michael asks, is the file upload part of the 80? Just so that we're all on the same page. It's the. So I don't remember if I answered Ginger's question. All of it will be in a single form. Today, I will send you guys an announcement with, I think I'm going to call it fake exam. To give you an option, there will be one multiple choice, one fill in the blank, and a here's where the other types of questions will be. I will allow it to auto grade so you can kind of see what the feedback will look like at the end. So Amanda asks, what happens if you've turned in 84%? You're okay. Everything's complicated. So in this case, for the pi score, if you only complete 84% of the pi at the end, you will get 84 points out of 100. If you've turned in 84% of it on time, you will fall into the next bucket, which I want to say is you get 80 points out of 100. It's in the syllabus. I will put it in this week's announcement. If you pop into my Zoom office hours, I'm happy to look at your ALEX and your ALEX alone and tell you what your score is. So Amanda asks, in the case that somehow your internet goes out because of rain, will Canvas pause the time? I have no idea. I don't think so. So I want to be real clear about what happens. If you lose the internet or anything else goes wrong, you need to send me an email. If it is between 3 p.m. and midnight and 8:30, and 5 p.m., you should get a response pretty quick, and we will handle that on a case-by-case basis. I know that Canvas has been particularly snotty. We are going to all just kind of try to do our best. I don't think Canvas will pause the time. I think it will kick you out, to be quite honest. And if that happens, just send me an email. Actually, first, take 2 deep breaths. Send me a panicked email. Take 2 more deep breaths, and I will contact you. If it happens and I have office hours, please hop in there. I'm happy to help. I promise we will figure out a way how to make it work. I can't make a plan for that because secretly I'm hoping that all of our internets behave. Okay. Oh, so someone asked, will you go through the Canvas questions, the questions that Canvas graded? Yes. I'm sorry, I forgot to say that. I will go back through those because Canvas is notorious for, let's just say the answer is oxygen and you put O, or you put oxygen and you spelled it wrong or something else. I will go back and we will double check everything. It will be the same. Partial credit can be awarded on the fill in the blank for the ways that we would have typically done that in class. Thanks, Megan. So Dakota asks, what time frame do you have to take the exam in? It will open Wednesday at 3 p.m. and the last possible time you will have to complete it is Thursday at 5 p.m. So between those 26 hours is when you have time to take the exam. If by chance you're watching this and you realize that in those 26 hours, you are going to work for 24 of them, please send me an email. I will do everything I can to work with you to make sure this works. Any other questions? Is there any other announcements? Oh, Megan's hosting her SI review tomorrow from 6 to 7 and on Wednesday. So Christina and Aaron have questions. Do you need work for the fill in the blank questions? No, you do not need to show work for the fill in the blank. Any partial credit will be awarded based on they'll be somewhat similar to the, I don't think there will not be the amount of questions as usual. I think so. It's structured quite differently, but right now it's 10 multiple choice, 12 to 15 fill in the blanky type things, and then I think 4 or 5 short answers. But we all know that I've never finished my exams before the day before it's due, so that's all I can tell you. Any other questions? Amanda, you are correct, but you forgot section 5.8, which is the, I'll just write that in the comments. And 5.8, heat of reaction using bond. So that's the only section that Amanda didn't mention. The usual announcement slides, I was just running a little late today, will go up today, and we'll put that in there. Any other questions before we look at what's left in chapter 9? If you have more questions tonight, I have Zoom office hours from 5:45 to 6. And I am more than happy to talk to you about this. I think I may try to upload a talking video into Canvas to kind of give you one last thing. So the last question, or not the last, you guys can keep asking them. Sam asked, when are your last objectives? So there are objectives from today due on Wednesday. Then there are objectives for next week that will be due on Friday. So you have 2 more objective due dates, Wednesday the 15th and the 24th. Then all of the pie needs to be complete by the 27th at 3 p.m. So you can finish that. The last, I want to say there's like 8 objectives due the last week. Most of you will be familiar with that material. It's the ideal gas laws. So there was a knowledge check due today. There is one next week. I have been requested, and I am still strongly considering removing the last knowledge check from next week so that you guys can just complete your pies as you see fit. And that way you'll be able to not lose any more objectives. So I am considering that. All right, any other questions today? Will the final be the same format as this exam? I think so. It will. So Aaron asks, will the final be the same format as this exam? That is the current plan. However, as I told my friends, if this is an epic dumpster fire, we will reevaluate. But it will be run through Canvas. There will still be some definition of time that it's open, that you can take it. Some part of it will be graded by Canvas. Some part of it will be graded by Dr. Malcolm. My hope is that this format works really well and we can continue to use that. But that is the current today plan. We are operating under that assumption that the final exam will be the same format or a given value of the same types of format than the exam 3. I'm sorry to be vague. I'm not trying to. I am very concerned, as you guys are, that this will be not what we intend. That will be too hard, too complicated, and everything else. So that's the current game plan. Any other questions? Sarah, you're right. It's not a due date. It mostly means that the knowledge check, I'm sorry to panic you. No, the knowledge checks open after certain ones. So on my list, it tells me that you have a knowledge check after the one that finished today. So you will have to do that before you go to the next one. That will never, under any circumstance, affect your turned in on-time grade. Those are just a separate thing. Good questions. Also, I'd like to you've forgotten. I wish that we were all standing at school together in the same place. Sorry, my internet said that it was having a glitch out. I'm sure you just watched me make crazy faces. But let's talk about chapter 9. Make sure that. So today we're going to continue to draw structures. So hopefully you guys spent some time over the last weekend or the last several days to really practice drawing things. So the first thing we're going to think about is on slide 14, titled acetic acid. So what you see is something that looks a little bit like this. We have a carbon connected to 3 hydrogens. Carbon, double bond oxygen with 2 lone pairs. Oxygen, 2 lone pairs. Oxygen, hydrogen. So we can work. Thomas, you're correct. As long as you finish this week's objectives, you have access to anything in the course. There is an open pie next weekend and then one the following weekend. So you have plenty of time to finish all of your Alex pie. So acetic acid. Hold on. This is not the right arrangement. Sorry. Life is hard. Okay. So this is acetic acid. If you were provided this Lewis dot structure, what I might ask you guys to do is to draw the 3D structure of the whole molecule. Now, likely you're like, Dr. Malcolm, that seems super hard. So the thing with this structure is instead of trying to look at the whole thing and ask, well, what does it look like in 3D? Just look at part of it. This will work better if I'm on this side. So if we think about this carbon and we ask ourselves, how many things is it connected to? Well, it's only connected to 4 things. So this carbon right here has a steric number of 4. Okay, well, can't see that. I think this marker is dead. Shoot. Hold on. There we go. So we have a steric number of 4. Okay. Well, we know what steric numbers of 4 look like, right? So steric number of 4 tells us that it's tetrahedral. Okay. So we could draw that. So we have our first carbon. And we know that tetrahedral looks something just like this, right? To where we have a carbon and 4 things connected to it. Well, that's a good sign. So what about if we look at this carbon in the middle? If we cover up everything else, 1, 2, 3. So we know that it is a steric number of 3. So steric numbers of 3 are trigonal planar. So we know that that is going to be connected to 3 things. Well, what are the bond angles of something that's trigonal planar? Okay, so they're 120. So we should be able to look at this piece here. And now we've been able to draw this framework, okay? So what I did is I know that, let me get a different color. Anything that I like to call up in the box, like this, anything that's connected in a row, hopefully you can be able to put it all in the plane of the board or the paper. So I connected the carbon to the carbon in the plane of the paper. Well, that's a good sign. So from here, we can put our hydrogens on this molecule. So now we have our carbons. So next to that, we have an oxygen that's connected to 1, 2, 3, 4 things. So this oxygen also has a steric number of 4. So do we think it matters whether we put it here or here? The short answer is no, they're about the same. Now, there are ways to look, but that's because I've been doing this a long time. You could put it here or here. They are both the same and they are both correct. Sorry, I can tell it buffers now. Correction, I have no idea when it buffers. It tells me my internet is unstable. So what I said was you could put the oxygens here or here. So I'm going to put this oxygen here. But then we also need to put all of the steric number of 4 around this oxygen. So we're going to add back in our double bonded oxygen. You can still see. It has 2 lone pairs on it. This oxygen has a single hydrogen and looks like this. So we've now been able to draw a complex molecule in 3D. So on the exam, I will give you a Lewis dot structure of a larger, more complex molecule, like acetic acid or something with a few more things. Instead of looking at it and saying, oh my goodness, I don't know what to do, maybe we should say, after we have the I don't know what to do moment, remember that each atom can be a central atom. So in this case, this carbon is connected to 4 things. The steric number of 4 tells us that it's tetrahedral. So we could go in and say tetrahedral. That's tetrahedral. This carbon here is trigonal planar. And this oxygen here is bent, if it asks for the molecular geometry for any of these. Is that, what do the lone pairs mean? So, Sam, the lone pairs, we have to indicate that they're lone pairs in a molecule. So last week when we did the E's, that is to show you where the lone pairs would be. In this case, for a molecule, we need to show where the lone pairs are, and we do that by just putting wedges and dashes for our lone pairs. Good question. Any other questions? So Thomas asked, is there a chart to know these names or do you need to memorize them? On Canvas, I posted this sheet right here in the Vesper table handout. So this is the piece that you're looking for, where it has all of the different drawings, the names, both for the base geometry and the electron geometry, as well as the bond angles. This is the page that you are required to know. When I send out tonight's announcement, I will put it in that for you guys to find easily. So the next thing we kind of want to think about, so we're going to start to talk about section 9.3. So 9.3 is molecular shape and polarity. So if we remember back to chapter 8, we talked about polar bonds. So we know that the oxygen-hydrogen bond is polar. We know that the negative charge is going to go in this direction. So oxygen, this is we're going to call it a polar bond. And we're going to use the electronegativity. In order to look at that. And so we know that elements that are a little bit further apart but still nonmetals have polar bonds. And that in this case, the arrowhead points to where the electrons are going, which is the more electronegative atom. So when we think about that, think about is what happens to have a polar molecule. So let's think about water. We know that we have H2O, where oxygen is our central atom. So we know that H2O has a Lewis dot structure that looks like this. So if you looked at the Lewis dot structure, the Lewis dot structure tells you that we have this arrangement. And so the problem is that that tells you that it's nonpolar. And the reason is because they both push in, and so they're at 90 degrees, so they don't really work. Except we know that water isn't a linear molecule. We know, based on Vesper theory, that water should look something like this. With our 2 lone pairs above. So when we think about this, let me make that go away so you guys can see. So we now have this structure. And so if we still have our same polar bonds, the question is water going to be overall polar or just some polar bonds in an arrangement? It turns out that water has an overall, so water, let me write this down. Water has let me make sure you can see it, a molecular dipole based on the arrangement of bonds. Good, we can still see that. Bonds. So what this is saying is that because this structure has two polar bonds that look like this, so they're pushing the electron density up towards the oxygen, the entire molecule has a polar orientation. We know this based on how water interacts with ions in solution, right? We know that it has a delta plus and a delta minus, and so this is telling you where that information comes from. So when we think about different molecules and different polar bonds, the way that you can figure this out is based on their 3D geometry. So if we look at, so the water dipole is on slide 16. So now let's look at CO2. We know that carbon oxygen, also is going to have a polar bond. So carbon oxygen is still polar. Well, that's good. Everybody, that's a great sign. But now we want to know if CO2, which is not the same, but kind of similar to water. So let's look at our Lewis dot and Vespers structures. So when we draw the Lewis dot / Vespers of CO2, it looks like this. So it turns out for CO2, the Lewis dot structure looks identical to the Vesper, but let's draw the other one. So in this case, the question becomes, is the overall molecule going to be polar? So because we have equal and opposite bonds, so both of these, you can't really bend my body in that way, but if the electron density is being pulled away from my elbows this way, it's being pulled at the same rate. So both of the polar bonds are in the same proportion, so this is non-polar. So even though carbon-oxygen is a superpolar bond, in this molecule, it's not polar at all. So the arrangement of the bonds in 3D shapes or spaces tells you whether or not they're polar. So when you start to draw things, you should start to ask yourselves, is this polar or not? So Amanda asks, for the Lewis dot structures that we draw in the exam, are they required to have a formal charge of 0? If they 0 charge, then yes. We'll do ammonia in just a second. So Sam asks, how do you determine which way the arrows go? So the arrows indicate the bond dipole, and they point toward the electronegative atom, and this came out of section 8.4. So the electronegativity scale that tells you that fluorine is the most electronegative atom, and it basically sprawls backwards in this direction towards the cesium, which is the least electronegative. So fluorine is always polar. Oxygen is frequently polar. So we were asked about ammonia. So now let's look at ammonia. So we have NH3, and we have a Lewis dot structure that looks like this. So we know that ammonia has a Lewis dot structure that looks like this. I'm sorry, it buffered, Amanda. Amaya. So for Lewis dot structures that you draw in the exam, are they required to have a formal charge of 0? Likely the most preferred Lewis dot structure has a formal charge of 0. Unless the molecule has a formal charge, you likely should have a neutral molecule. Does that help you answer your question? So ammonia. We have a steric number of 1, 2, 3, 4, which makes it the molecule is the base geometry is tetrahedral. Which looks something like this. So from here, we now can put on our 3 hydrogens and the lone pair. These are all equivalent at this point, so you can put them anywhere you like. It's okay. It's probably my internet. I'm so sorry. So we're going to add our hydrogen molecules here. We're going to put our lone pair at the top. So in this case, this looks somewhat similar to methane, but when we think about the dipole moment of ammonia, we know that all of these have a dipole moment for the ammonia bond. So the overall dipole moment, there is a dipole moment, and it goes in this direction. So it points towards the lone pair. Yeah, cloudy skies, storms. I'm secretly hoping it doesn't rain because I am definitely afraid that if it rains, we will have no more class. So here's hoping we can make it for another 30 minutes. So in this case, ammonia does have an overall polarity because all of these 3 bonds push together and the overall electron density goes towards the lone pair. So usually I think about bond polarity as playing tug of war. So the more electronegative atom yanks on the electrons and hoards them, okay? So that's what electronegativity means. It basically draws them in. So when we think about something in this arrangement, nitrogen pulls all of the electron density from the 3 hydrogens. Not in total, just a little. The thing is, this lone pair up here also drags the electron density. So basically what we see is a shifting of the negative charge towards the lone pair. So we see that. So if you have this molecule instead, BF3, that looks like this. So BF3, we have a trigonal planar molecule. Now all of these are polar. And we know that fluorine is the most polar. So we assume that they're all going to look like this. It turns out that this molecule, this is polar. So the reason that BF3 is not polar is because all of these pull in the same direction. So in this case, when they pull all of them out, they pull the same amount. And because they're at 120 degrees, exactly spaced apart, in this case, none of them are going to be any more polar than the other. So electron densities, when we think about polarity, is about balance. All of these are the same, so there is no polar molecule. If you were to swap any of these out for a hydrogen, then you might be able to have a dipole moment for the full atom. So the next thing we're going to talk about into 9.4. So if you have a question, go ahead and drop it in the comment box as I erase and think about 9.4. So 9.4 is orbital overlap. And what orbital overlap tells us is that in order for two electrons to make a bond, so we know that two electrons make a bond, the two electrons must reside in overlapping orbitals. So what this is basically telling us is that the two orbitals have to overlap in order to create a bond. So if you look at slide 18, it shows you a graphic that looks like this, where we have R on the bottom, and then we have energy increasing. And so what we see is something that looks maybe not that high, a little bit like this. Now, this tells us that the radius, there's an optimum radius. So this is our bond length. We still see it, yep. So basically, if we think about trying to add two orbitals together, there's going to be an optimum bond length. We've learned this in chapter 7. So we know if we try to shove them any closer, the nuclei are going to start to repel each other. That happens here. So nuclear repulsion. Out here, they're basically so far apart that they can't feel each other. So here, we're too far apart. So this section really just tells us one thing. Basically, it tells us that when the atoms are too far apart, they can't interact. When they're too close together, they basically fight for space. So in order to create a bond, two electrons or more have to interact favorably, and they do that by the orbitals just overlapping, kind of like this. A little bit of overlap allows us to create a bond. So the next section is going to give us the ability to think about what it means to create a tetrahedral shape or a trigonal planar shape, and where on earth do double bonds even come from. So again, if you have a question, feel free to drop it in the comments, and we are going to try to get through this and talk a little bit about multiple bonds, and then we are going to do a few more examples if we have time. So the next part, starting on slide 18, and I think there are just 5 or 6 questions, and so, or 5 or 6 slides, is to talk about hybrid orbitals. So hybrid orbitals. Here's the thing with hybrid orbitals. We know that we have 3 p orbitals. Mr. Virtualizing Reality, I'm pretty sure you're a bot, so I'm going to ask you to go. You're going to be in timeout. So, we know that there are 3 p orbitals. This week I brought some raisins. Good suggestion. So we know that there are 3 p orbitals, the px, py, and pz. Oh my God, oh my God. Okay, I guess we're all stuck with that. So we have three p orbitals. P orbitals we know are px, py, and pz. This didn't work. I don't know. I'm really sorry. So we have three p orbitals, px, py, and pz. So what we can see is that these three orbitals, none of these make any of the shapes that we've seen before, right? So in this case, px, py, and pz, they don't really make any of the structures that we've seen. So hybrid orbitals are going to allow us to mix these into something different. So when we make these, we're going to take our px, py, and pz and the s orbitals and combine them into something else. Now, hybrid orbitals allow us to create bonds in a different structure. So hybrid orbitals mix orbitals together to form, we're going to say, new shapes. So the thing with this is when we create new shapes, that is a great way for us to get some of the structures that we've seen. So hybrid orbitals in Gen Chem 1 only create a certain number of things. So if we look at slide 20, we're going to hybridize orbitals. So in this case, when we create this type of content, we're going to mix them together. When we mix them together, we're going to put in a specific number and we're going to get out a specific number of orbitals. So orbitals in equals orbitals out. So if we mix together three orbitals, we're going to get three orbitals out. I'm with Sarah. I'm trying to ignore it. So I know I'm trying hard, guys. So what we mix in is what we can get out. So if we look at slide 21, which is called hybrid orbitals, in this class, we're really only going to look at sp hybridization, sp2 hybridization, and sp3 hybridization. So I did that, Kelly. We're going to see what happens, but I'm trying not to feed anything, so we're just going to all. I think it left, but we don't know. So we're just going to move on. So in this course, we're only really going to talk about three types of hybridization. So we're going to look at sp2, sp2, and sp3 hybridization. Likely, it's possible that you guys have heard about dehybridization. At UNF, we don't use dehybridization. sp dehybridization is often found in some textbooks, true life, true stories. Different faculty believe in it and different people don't. At UNF, we don't use it, so we're not going to talk about it in this class. So we can really only have sp, sp2, and sp3 hybridization. So for sp hybridization or sp2 or sp3 hybridization, we're going to start with sp3 and work our way backwards because I think that makes the most sense. So for sp3 hybridization, we're going to use this, or we find this in things like methane, so CH4. Now, if we look at the electron geometry, the electron configuration for carbon, we know that carbon has 1s, 2s, 2p, So, whoops. So this is the electron configuration for carbon. Now, if we want to create a bond, we know that 2 electrons have to come together, and those 2 electrons are going to make a bond. Well, it only looks like you could get 2 of these, because these are the only 2 available seeds. We know that methane exists. So hybridization says that we're going to take these 4 orbitals, we're going to hybridize. Now, I like to think about this as like if you're going to make maybe not a protein shake, but like a blended acai bowl, right? You put a bunch of stuff in the blender and you blend it up. If you blend it up well, there are no leftover chunks. So what we're going to do is we're going to mix these together and we're going to get out 4 identical orbitals. So we added together an S plus a P plus a P plus a P, okay? So now what we have is sp3 orbitals. So this statement here, S and then the letter P with a superscript 3 tells you that we mix together 1 S and 3 Ps. Our 4 electrons are going to be right here. So now we can easily bind in our hydrogens with the 1s electrons, and they can bind here. So when we create methane, we have a molecule that looks like this. So this carbon center here has an sp3 hybridization. So no, it's not that they overlap. It's that we mix them together and create 4 new identical orbitals. So for an sp3 hybridized orbital, it creates 109.5 degree angles that we see in tetrahedral. So now you don't have to use all of these, but you can. And this is what we see. So this is an sp3. For anything with a steric number of 3, nope, 4, it is sp3 hybridized. So everything that is tetrahedral, bent, trigonal, pyramidal, all of those are sp3 hybridized. The trick is whether or not they have lone pairs in any of their orbitals. The H is the hydrogen here. So now we can mix together these 2 mix to create a bond. Hydrogen is a 1s. So we know that hydrogen just has 1s. Yes, I'm combining them both in order to do that. How do you determine which way the arrows go? So you might not remember, but in this case, you can put them up or down. Yes, so at the end, we mix these, or these 2 make a bond. So when the 1s and 1 of the sp3 hybridized orbitals mix together, here and here, what happens then is now we can make a bond. Because in 9.4, we learned that they have to overlap. So there isn't really a final answer yet. So if I were to ask you, what is the hybridization of methane? Because it has a steric number of 4, it has to be sp3 hybridized. So hybridization basically says that we take them together and mix them in order to create the bond angles that we know. So now let's think about sp2. So something that makes, let's look at, so let's look at BF3. So if we look at BF3, we know today already that this is going to look like this in 3D space. thankfully, we also know that none of our p orbitals allow us to look like this. So in order to create this structure, which we know exists based on crystallography data, we need to hybridize these orbitals. So the question would be, what is the hybridization of boron in BF3? So this would be the type of question that you'll find both in ALEKS or on my exam. So in this case, so sp2, promotion of one electron in the s orbital to one of the p atomic orbitals. No, we don't promote electrons, we mix orbitals together. So in this case, we know that boron has a 1s, 2s, 2p. It has 3 valence electrons that look like this. So if you promote one here to where you have 2 in a p and 1 in the s, the problem with that is it's still not the correct arrangement. You have 2 at 90 degrees to one another, and then you have 1 in a spherical orbital. However, if you hybridize these orbitals, so we're going to mix together an s plus a p, which gives us the sp2 orbitals, to where we have sp2. We now have this arrangement where the 3 fluorine atoms can interact with these combined sp2. It is super important to know that we have leftover p orbitals. We have 1 leftover p orbital. And we might get to talk about that. But you will need to watch the YouTube video on multiple bonds, which talks about how these leftover pure p orbitals can create the pi orbitals, or the double bonds that we've talked about. So right now we've talked about, for steric numbers of 4, we have sp3 hybridization. For our steric numbers of 3, we have sp2 hybridization. So the last one we're going to talk about is sp hybridization. So if we look at sp, so we're going to talk about CO2. So we know that carbon dioxide looks like this. Look at carbon. Okay, so we have the same thing that we had previously. So ordinarily, where does the second? So we mix together, for sp2, you mix together 2 p orbitals. So one of them was empty, but we used it to mix to create equivalent orbitals. So hybridization, you basically put in what you want to get out. So if you need 3 orbitals, how are we adding it to get the sp? So to create the sp orbitals, we're going to do something different. So we're going to create, we need equivalent orbitals that are apart. So in this case, we're going to mix this plus this. Now, previously we mixed together all of them. So to mix the sp, we need to be able to create bonds that are 180 degrees apart. We know that this structure has 2 double bonds. Double bonds, as we will come to find out, require pure p orbitals. So we're going to leave these alone. So when we mix them together, we get our 4 electrons. These are our sp hybrids. And these are our pure p orbitals. So now we have 4 bonds. So Amaya, can you restate that question? What do you mean, how are we adding it up to get the sp? So if you have a steric number of 2, it has to be an sp hybrid, because that's when you multiply them together, you get a linear bond. In this case, we're going to hybridize, mix together. You don't add, you mix the 2s and the empty p orbital to give you equivalent sp orbitals. Then there are 2 leftover pure p orbitals. Pure p orbitals, as you'll find out in the YouTube video, allow you to create double bonds, because double bonds, it turns out, are not the same as a single bond. So we have single bonds that will be internuclear, double bonds are above. But you'll be able to watch that YouTube video between now and on Wednesday and look at those. So in my course, so steric number of 3 has sp2 hybridization. Yes. So Sam asks, why are there 2 pure p left over when there's only 1 above it left? So Sam, I mixed this one and this one to create these 2. These 2 stayed the same, and so I left them alone. So to determine the hybrid orbitals, it's, I don't want to say quite simple. There are more complex ways to do this. But if you look on your graphic, all right, come here. Sorry, Lily decided she's ready to come to school. I'll show you guys in just a second. Baby. So for Gen Chem 1, on your table, the last thing is the hybridization. If it has a steric number of 2, it is sp2 hybridized. If it has a steric number of 3, it requires 3 equivalent things, 1 s and 2 p's. For steric numbers of 4, it requires 1 s and 3 p's to give you sp3 hybridization. That is the best way for you to think about this. So next, for the last 5 minutes, on slide 23, it asks, what is the hybridization of the underlying atom? So we just did CO2. Then there are 3 others. So you could look at BF3, PCl3. I'll write these up here. Okay. So how are we getting S plus P for the sp2 when we only had 1 electron in the 2p? So if you think about for an sp2, so we have in the S, and then in this case, our p orbitals. So when we mix together this 1s, we mix together all 3 of these to make 3sp2. So I think I get your question. Hopefully this answers it. So if we mix together these 2, just the s and the p, we still don't have enough single occupant orbitals. In order to make a bond, 2 electrons have to come together. Those 2 electrons have to come from different orbitals. But they can't, like this s right here already has 2 electrons in it. Those 2 electrons can't overlap to make a bond because they're already, both seats are full. So what we want to do is create 3 degenerate, meaning equivalent orbitals. And we did that by mixing together an empty p, a p with 1 electron, and an s with 2 electrons. So now we have 3 equivalent orbitals and a single leftover p orbital. Does that help answer your question? So for the last couple of seconds, I think what we'll do is we'll try to do a few more examples. Don't forget that there is the Vesper handout for the Vesper, there's a table in the Vesper module that basically is a bunch more examples. The way that you can become more, like, not happy with this, but the way this is a little bit easier is if you go through and practice. For anything tetrahedral, so steric number of 3 or lower, you can have hybridization. Steric numbers 5 and 6, there is no hybridization. So all we can ask is, what is the hybridization of this orbital? So you can determine that by determining the steric number. I'm glad to help. Sorry for the confusion. So let's look at some of these examples. So let's look at, we're going to start with PCl3. So the first thing we want to do is draw a valence Lewis dot structure. So we know that there are the valence electrons will be 5 plus 3 times 7. So that gives us 26. So we're going to make a structure that looks like this. We're going to create octet on all of our exterior atoms. So now we've used 8, 16, 24. We have 2 left over. So our last goes here. Yes, the leftover P can form pi bonds. So in this case, this is our Lewis dot structure. From here, we can draw a Vesper structure. So you can determine hybridization either from this structure or from the Vesper structure. So if there are 1, 2, 3, 4 things connected to phosphorus, we know that the base geometry has to be tetrahedral, okay? Now the electron geometry or the molecular shape is going to be different. So we know it's going to look like this. Then we can draw our chlorine atoms. They look like this. We have this here. So in my class, you are required to show all of your lone pairs all of the time. So the question asks, what is the hybridization of the phosphorus? So because we have 1, 2 mixed together like this, the hybridization of this is going to be sp3. Hybridization is about just for what it is. So if there's this molecule, you can look at this in this case. Yes, so AB3E is tetrahedral, but the molecular shape in this case would be trigonal pyramidal. And the bond angles would be less than 109, as opposed to much, much less than 109. So are there any other questions? Because this plus the YouTube video that you need to watch tonight. So I'm going to send you an announcement that has the following. A link to the multiple bonds YouTube video, which you can also find in chapter 9. A link to the table that I think Thomas asked about earlier. I will post a direct link so you can download this. I will also try to give you, I will give you a practice quiz. You don't have to do it. It's literally going to be, here's a multiple choice, here's a fill in the blank, here's what it would look like where it tells you what to do for the upload documents. Just so that I think my hope is that that will give you a little bit less anxiety about how to do the next part. Anybody else have any other questions? Hey, Lily. And because everyone is concerned, here's Miss Lillian. Whoops, no one can see her. She's so cute. She's been really tired with the rain. If there are no other questions, and I'll hang out here for a second to see if you have them, I'm available in my Zoom office hours tonight. Glad to help out. for anything you need. Otherwise, I will see you all for our exam on Wednesday. If you have technical difficulties, please send me an email. If you want more help, hit up SI. Otherwise, I will see you all next week. There is not a chart for the hybridization, but in the chart that you could have filled out, anything with a steric number of 4 is sp3 hybridized. Steric number of 3, sp2. Steric number of 2 is sp hybridized. That's all there is. It feels more complicated than it is. Sorry, there's not a table. Any other questions? Glad to help out. I miss you guys. I hope you're having a great rest of the day and you don't get rained on. Bye, guys. Feel free to stop in office hours tonight.